Thanks for the introduction. And this is some work coming out of internship project that Lawrence Day from Nottingham University. He joined us for 3 months and did this project. And it's also joint work with Neil, Todd, and Raj from Intel Labs. So let's first start with a problem statement. We want to write programs that run on GPUs. I don't know much about you, but at the place I work, we want to be a little bit more specific. And look at integrated GPUs, because we don't do discrete GPUs. So why is this interesting? Why is this problem interesting? It's because integrated GPUs, they are everywhere. They require much less energy than the usual CPUs. And also, if you look at this diagrams, they are actually taking a much larger place on die. Right? They're getting a lot of support from the chip vendors, and they're becoming a lot faster. They have more cores on the GPU side than the CPU side. And most importantly, the GPUs and CPUs, in an integrated GPU, they share the main memory, and sometimes they share the NOS level cache as well. So what makes this problem challenging is GPUs are designed to be different. They're designed for throughputs. They have a much larger number of core counts. And they have this single instruction, multiple thread execution model where all the work items in a particular work group, they execute in a lockstep. So, and also there are some other differences, like they have a very shallow pipeline, they don't do well on branches. Because of all these differences, it makes programming GPUs a challenging job. So different vendors, they have come up with different low-level solutions like CUDA and OpenCL. And as a logical consequence, we have to program differently for integrated GPUs. But if you look at this, something doesn't really look right here. As a strongly lazy type, we don't want to program differently. Instead, we want to write the same program, but compile differently. So with that in mind, people actually come up with one of the most popular approach is to continue to write this declarative and high-level programs we used to write, and preferably in the functional language. And so this is a typical component of this kind of compilation flow. On the top, you have user program written in a DSL, and this DSL is implemented as a compiler in the host language. And the DSL compiler compiles from the user DSL program into OpenCL or CUDA that runs on GPU. But at the same time, the host language can compile through the traditional means to the CPU. And there's some runtime support to support the exchange of control and data between the two different executions. So as with any programming model, pros and cons. The pros is that you continue to write in a highly declarative way with high-level constructs and operators. And you can do domain-specific optimizations for GPU for this particular target. But there are also cons. One of them is there's barrier between the DSL program and the host program. Sometimes you want to exchange data and you want to call foreign function interface. There's some kind of barrier you have to overcome. And also, a lot of times we have domain-specific optimization, but we also want the ordinary optimizations for general purpose programs. And they are not available in the DSL compiler. So oftentimes we have to re-implement some of the general techniques we use. So here we just want to take a step back and explore a different approach. What if we can just compile the subset of the host language directly to GPU target? This is in particular less explored for functional languages. But by doing this, we get to enjoy all the optimization opportunity available to the host language. And with the new OpenCL standard, there's shared virtual memory support, which makes this approach a lot easier. So in this talk, we're focusing on this native offload of Haskell Repa programs to integrated GPUs. I'll first give an introduction, a small introduction to Repa library if you're not familiar with. So here we have a little program where we declare this A as unboxed array. If you look at the type, is array of U. U means unboxed. It's a two-dimensional array that's dim2, and it's constructed from some kind of generator from a list, which has the dimension 5 and 10. And then we compute from A to get some result of B. And B here, if you look at type, it's different from A, but it has the D annotation that is indexed differently. So B is actually an abstract representation of computation arrays. So this is not actually the computation. Here we do a map and then do another map. Is not actually performed until the time you wanna say I wanna run it in parallel on B. All the delayed computations you have in B, I want to run it and give me back an unboxed array that has all the results stored in C. So this C, if we use this compute P API, it means just go off and run it in parallel CPUs. So that's roughly how Repa works. There's a lot more details. Some different abstract representation of arrays. You can do very fancy stuff. Important observation we have is, why not just replace this compute P with compute G, so that just go off and run this computation on GPUs instead of CPUs. So to do this, if we introduce another API, compute G function, that give it identical signature to compute P, you don't have to worry about all the type class and stuff. But the important point is we want compute G to do the same thing as sequential computation compute S, parallel computation on CPU compute P, to behave semantically in a similar way. So in theory, all Repa programs should also run GPUs, right? If we just replace compute P or compute S by compute G. But there's more than that. In practice, it's pretty challenging, especially when we are talking about Haskell, which is a lazy language. So we only target a restricted subset, and only this subset is allowed to compile and run. I'll go back to this point in a few slides. First, we'll look at how this compute G is implemented internally. We introduce a primitive operator called Offload that takes an upper bound of a range. Basically, we're assuming a linear kind of index space. And the second parameter is a kernel function that maps from index to the range, in a range to a stateful computation, where you see this state hash S. That is actually, if you're not familiar with internals of GPC, that's actually how I/O monad is internally implemented. So it turns out this introducing this one additional primitive offload is enough to implement compute G. I won't go into the details. but here just give you an overview of the overall implementation we have done. We chose to implement this in Intel Labs Haskell Research Compiler for the reason because this compiler can output programs very similar to C, where GPC doesn't really do that anymore. So this work was presented last year in the Haskell Symposium. And also we make use of another compiler called Concord, which is by another group in our labs. This Concord is actually open source. It compiles from C++ programs to OpenCL and make use of this shared virtual memory support. So first we modify Repa to implement compute-G in terms of offload primitive. Then we modify GPC to introduce the type of this primitive and leave out the implementation because eventually we want to catch this primitive in our HRC compiler backend because HRC invoke GPC first to compile whatever source language to external core. Then we take external core and go through HRC compiler to turn it into a form that's similar to C. And then we use Intel compiler to compile it for CPU. In this case, we would like to use Concord to compile it to OpenCL. So after we intercept this cost to offload primitive by looking at intermediate form in the program, we dump the kernel function to a C file. Then we just use Concord to compile that to OpenCL. And the last step is to replace the offload call in the main program to some Concord core into Concord runtime so that at runtime you will invoke this on the GPU. So this seems pretty straightforward. And what's the catch? So like I mentioned, we can only do a subset. Not all Repa functions can be offloaded. One of the first limitations is that we must statically know at compile time which function are you really want to offload. If you have a very dynamic program that creates a runtime closure or some dynamic function pointer and just want to offload that, we cannot support it. So some other additions to this is we don't allow any memory allocation. We don't allow any thumb evals like lazy evaluation. We don't do that. We don't do recursion. We don't do exception. A lot of restrictions. It may seem overly restrictive, but it's actually not. So there are some. Additionally, we to simplify our implementation, we choose to allocate all the memory in the shared virtual memory space. And we insist that no garbage collector just suspend it while we're running this offload function on GPU. It turns out that this is actually not really that bad as it sounds. We can actually compile and run a lot of Repa programs. We took the set of benchmarks we presented last year in FL in this Haskell gap study. And it turns out most of them, they just compile and run fine, just fine on GPUs. So here we measure the performance on different hardware. This HP 4600 is integrated GPU with Core i7. It has 20 cores compared to 4 CPU cores, and it runs at much lower clock rate. But if you look at peak performance, these theoretical data flops, they're actually pretty similar. But the GPU runs at much lower power consumption. And then we also compare with the same set of programs compiled on Xeon server CPU, which has a lot more cores and has much better peak performance. So the result is actually pretty encouraging. If you can look at the paper for more details. We actually give a fairly detailed analysis in the paper. But here is just a summary. Average relative speed up compared to a single-threaded, single-core program running on Core i7. The average speed up from the GPU is 6.9. On the CPU is 7.0. They're fairly close if you look at peak performance. It's actually to be expected. The GPU runs at about 1/3 of the power consumption of the CPU. And if you look at the Xeon server-grade CPU, theoretically it has a lot more power, but it doesn't really perform that well if you consider that.
So where exactly do we see what the GPU does here and what the CPU
yes.
cores do?
The runtime we measure is the kernel running time. So it's entirely just computation over GPUs. Mm-hmm. And we measure the same kernel time on CPUs. We don't consider this preparing for the input and getting output. We don't compare those times. It's entirely about performance. It's not about data communication.
So all of them are OpenCL runtimes, is it? The one
no.
on the CPU?
No, the thing on CPU is compiled for CPU target. It's not through OpenCL.
Okay.
Quick question on the experiment setup. You said the baseline is a single core i7?
Yeah.
And you had the core i7, that's the same one with 4 cores being
Right. Yeah.
7 times faster?
Yeah, this is taking account of the you actually have SIMD vectorization.
And the single core one didn't do any SIMD vectorization? The
Right.
baseline?
Yeah.
Ah, okay. Thank you.
So what we have learned from this study is that laziness is not really a huge problem for especially for Repa programs, for these performance-oriented programs, because they are most likely strict in nature. However, we still do observe some things in the intermediate result. If we look at this previously I showed this very simple program, Repa program. This is part of the IR. After we run GPC on this program, all the optimizations GPC does and all the optimizations in the Repa library, and we translate that core to a strict form so that thunk allocation becomes explicit. If you look at this, there is actually still some dangling thunk allocations, and also there's still some box operation, just boxing data up. This stuff wouldn't really run on the GPU, so HRC compiler backend is able to optimize all this away, and when we get to the point of the IR in HRC, we can see that this entire function is the body of this toy program, and there's no thunk, there's no memory allocation. Is all just strict function, strict computation, mathematical computation, and some data fetching. And if you look at this, C output is annotated with types, but it's more or less the same as new IR. What we have also learned is many optimizations for CPUs also can help GPUs. Some of them, they're enabling factors for this project, because without them we've never been able to run this function directly on a GPU, like strictness analysis, like unboxing, like quantification that turns tail recursive calls into local control flow, like nested loops. So without them, we won't even be able to run this program. But even with that being said, some other optimizations they equally apply to GPUs. Here I just want to give a very simple example. We all know that GPUs, they do pretty bad on branch code. This is why. is because they execute in log steps. So some of the cores of GPU, when they execute, if this first condition is satisfied, the true branch, only some of them will be able to proceed, because the testing may not be true for the data for the other cores running the other threads. So the other threads will just sit idle. And similarly for the fourth branch, when the fourth branch is executing, the true branches there just sit idle. So there's a waste of computation power here. It turns out this branch problem is particularly serious for GHC compiled programs. This is because GHC tends to inline aggressively into the leaves. So we end up with a program that contains fairly large number of lines of code in each of the branches. So this is bad for actually both CPU and GPU. These branches, they share a lot of common expressions, modular alpha renaming. They are only a little bit different. So, but this is not really a concern for GHC, because GHC, if executing this code sequentially on CPU, there's no significant cost. But previously, when we do the study on the NinjaGAP programs, we realized this is a problem for SIMD vectorization. So we implemented this branch to conditional move optimization for the CPU. It turns out this is great for GPU as well, because we can avoid branches. We can reduce the lines of code in each branch. But not always rosy. Sometimes we must optimize differently. Since I'm running a little bit over time, so this is an example of 2D convolution. Basically, you compute the new value of a pixel based on the surrounding pixels. There's a very nice Repa paper talking about optimizations for CPU, so that you can, if you group this block computation together, you can actually save on the memory reads. So this is great for sequential speed up on CPU, because it is cache friendly. But for SIMD, actually not much, because it does this in a horizontal way. If we do vectorization, this creates stripe load. So, but there's an easy fix.
You mean scatter gathers? Like that is the issue, that you can do with block rewrite versus you have to scatter gather into a block?
Right, scatter gather is it was not implemented in hardware previously, but now we have CPU support that. So for SIMD, we did a very small change. We block vertically instead, then we can do sequential loads for the vector. But for GPUs, this is actually pretty disappointing. There's a huge slowdown. You can read the paper for detail. It turns out that if you don't do any block reads, it actually got faster. So the conclusion is the advancing hardware gives new opportunity to explore alternatives, like what we did here due to the recent support for shared virtual memory. And native, we hope to show that native offload is a viable approach, and optimization for GPUs is both challenging and fun.
We have time for some quick questions. Yes, please.
In the worker functions that you pass to the Repa combinators, can you compile code which uses algebraic data as well as just numeric primitives?
Mostly numeric primitives. Algebraic data usually involves allocating memory. So
can you compile code which reads algebraic data? So I have an example that's a ray tracer in Gloss, which uses Repa to distribute the workload, and then the wrapper of the Repa computation creates the scene graph. but the worker functions only read, they don't allocate.
That's definitely true for Repa programs. Repa programs, they're pretty flexible. You can have a lot of different things. You do a lot of different things in there. One of the problems we might have in this case is that those data structure might be first of all boxed. There might be stock allocation. So if you just read from it, may not be a huge problem.
So what about if you had a worker function which was doing numeric computation but also reading from a shared array? Can you handle that?
Reading from shared array?
Like suppose you had a worker function which in its closure had a pointer to an array, and you pass that worker function to a map, and every map iteration was, say, indexing into the...
That's no problem.
That's all right?
Yeah, that's all right.
Okay, in the back, please. Last question.
Did you compare to Accelerate?
Well, we couldn't because Accelerate doesn't really have a functional working OpenCL backend. We would like to
run on an NVIDIA GPU.
we haven't tried other architecture. It's just Intel.
Rob, first, please.
Actually, I had two questions, but actually that was my first one, but it was to compare against Accelerate's CUDA backend. And my question is, why did you choose Repa as a vehicle for an OpenCL backend and not Accelerate as a vehicle for an OpenCL backend?
The point I was trying to deliver is that we take we don't take a DSL approach. We take just ordinary Haskell function. In some way, you can view Repa as a DSL for array computation, but it's a lot more flexible than Accelerate. On the other hand, Accelerate is a deep embedding, and you can actually do a lot of targeted optimizations in Accelerate. We wish we could compare the performance, but if you run something on OpenCL on the Intel GPU, and then you run something in CUDA on the NVIDIA GPU, it doesn't really make a lot of sense to compare them.
So, did you encounter any optimizations that GHC or HRC does which are no longer valid for OpenCL? For example, it doesn't understand that threads are now working in groups in lockstep. So things like loop unswitch aren't valid for OpenCL. But I don't know if GHC or HRC does that kind of thing. So did you encounter anything like that?
Loop on switch actually is valid in OpenCL code, but it just perform badly. We do some optimization of that. I mentioned this to conditional move conversion. We haven't really encountered anything that will be invalid for OpenCL target, but something it could lead to bad performance.
Okay, let's thank the speaker.